Welcome back, ladies and gentlemen. So, today, what we're going to talk about is really we're going to put together all of the different lessons we've kind of covered the past couple days. All right. And what we're going to do is that this particular video is going to focus on just kind of applying everything we've talked about in terms of things moving at a constant velocity, how we can model their motion, whether we're using a position time graph, a motion map, or this new velocity time graph, all right, that we just talked about in our previous lab. And we're going to use these kind of to model a real world situation. Now, of course, I know right now that it doesn't seem very interesting because the only things we ever seem to talk about are things moving in a straight line at a constant velocity. All right. And part of the reason we start with this is because we want to understand the very basics about how things move. Because once things start to get more complicated, we're going to use the exact same skills we've developed in this unit and we're going to apply them to more complicated motion. All right. What we're going to find out in this class is that as we move forward this year, we're going to take closer and closer steps to reality. All right, so right now we're in a very simple reality where everything moves in a straight line at constant velocity. And by the time we get to the end of the year, we'll be closer to reality, I suppose. We will be closer. You'll still see, if you continue to pursue physics beyond that, you'll see there's still a lot more reality to get to before we get to this. But I digress. So, with that being said, once again, this is another one of the worksheets where I think it would be awesome if you are working at this from home, if you can find someone else to work with. So either, FaceTime, Zoom with someone else, Google Hangout with someone else, or, if you want to make a Canvas group, I don't know if you can do that, but any of those things would be useful just because sometimes this sort of stuff is really useful for just practicing. All right. So I'm done prattling on. Basically, what I want you to do is you're on worksheet 4 of the packet right now. All right. And what you're going to do is you're going to first start with this question 7. And I want you to decide of these 3 scenarios, which scenarios does constant velocity model apply? So which of these scenarios basically is the object seem to be going at constant velocity, and which of these scenarios is the object not going at constant velocity? All right. And I basically want you to kind of pick which ones CVM applies, which ones it doesn't apply for, and then give a reason as to why you picked your answer. All right, so take about 4.5 to 5 minutes and 3 seconds. Pause this video, write down your answers. When you're ready, unpause it, and we'll talk about it. All right, so hopefully you had a chance, ladies and gentlemen, to kind of work through the first part. So let's kind of scroll down and see what we've got here. All right, and I'm going to minimize this a little bit so we have some space. So for part A, we wanted you to start by just saying if the constant velocity model, and I know it says constant velocity particle model, don't worry about it. It's just the constant velocity model. We want to know if it applies or not. And going through the 3 of them, you should have seen that only one of the 3 actually has constant velocity. All right, so if we start with the first scenario, we have a Mack truck. It starts from rest. That means it starts from a velocity of 0, and it reaches a speed of 8.5 meters per second in 20 seconds. All right, now, what we find out is that right away is not a constant velocity because the Mack truck has a different velocity from when it starts and when it ends. And when we go into our next unit, we're going to start to see the tools that we can use to look at something that's motion is changing, because in this case, the Mack truck is speeding up. All right, so for number 1, it does not apply. There is no constant velocity model here. For number 2, all it says is a dune buggy travels for 20 seconds at a speed of 8.5 meters per second. Well, right away, that seems pretty simple. There's not much there, but that's really useful to us because that's exactly the definition of constant velocity model. All right, so for number 2, constant velocity model does apply because it's traveling at constant speed. All right, and then for number 3, once again, I have a driver seeing a deer in the road ahead, and they apply the brakes. Now, those brakes are doing something. We're not quite sure what that is yet. In a couple of units, we'll talk about exactly what's happening here. But why that matters is because it says the car slows to a stop from 8.5 meters per second in 20 seconds. So just like we saw before, once again, the initial velocity and the final velocity are different. So that means this is not a constant velocity throughout. So constant velocity model does not apply here because the car is slowing down. All right? And that's what we want to start doing in physics. And when we get to certain parts, sometimes the math can be a little confusing. And for some of us, we're not big math fans, and that's totally fine. Because honestly, at the end of the day, when we do stuff in physics, the most important thing I want us to be able to do is to look at a situation like this, think about it, and tell yourself, oh, this thing is happening. So in this case, you're looking at a scenario and you're saying, oh, that object must be going at constant velocity. And we're going to learn throughout the year why things like this are important, because we're going to find out there's a lot of information hidden in this model that we don't know about yet that can tell us a lot about what's going on. All right? So that's part A. For part B, it says choose one of the problems for which CVPM applies, which right away, of the three, we know that only number 2 has that. So basically what you're going to do is you're going to look at part 2. I want you to draw at least 3 diagrams and or graphs to illustrate the situation. All right? So what that means is that I want you to draw 3 different diagrams or graphs that can like model the motion of that doom buggy. All right, and let's just kind of review ourselves to remind what's going on here. Some of the tools we have. We have a position time graph. That's the first thing we learned about with kind of modeling the motion of an object. We have this new type of graph, a velocity time graph. Might be really useful here. We also have a written description, which actually don't do that because it's already written down for you. All right, and then we also have a motion map as well. So right away, those are 3 things we can use to kind of model the motion of this object. And the reason we're doing all 3 is, for 1, just to practice using them, and 2, to understand that we can have for the same type of motion, we can have different ways we can show that off. All right, so there's multiple ways to get to the same answer. So same deal, pause this, take about, 4.5 to 5 minutes to answer this question as well. Remember, the most important thing you need to do in these notes, and I will definitely check this, is that you must draw straight lines when there are straight lines required. All right? So make sure your axes are nice and straight. Make sure anything that involves constant velocity has a nice straight line. Please do not try and tell me the little squiggle you scribbled in the last 5 seconds is a line, because I will look at you, smile, and I will say, get that out of my face, and we'll keep going and have a wonderful time. So with that being said, answer part B, please. All right, so hopefully a chance, ladies and gentlemen, to go through and draw some new diagrams and scenarios. If I scroll down, I have a position time graph and a velocity time graph for this situation. And then I apparently got bored and just doodled a little car. This is the master key from a couple years ago, so I have not updated it. So hopefully you saw that because this is a constant velocity, you knew that your position time graph needed to be linear. All right. Now, remember, when you draw graphs, and this is something where I didn't really explicitly tell you this before you started this question, but you need to include some key data points. All right, because sometimes it's not enough just to draw a graph. If I just drew a line, but I didn't have anything included with this, I really don't know much about what's going on here other than the fact it's a constant velocity. And because the question tells us some stuff about maybe the time it goes for and how fast it's moving, we can figure out a little bit more about this graph. All right, so when I label it, I can label the time at the end of it. It's 20 seconds. And I also can kind of work to figure out how far I've gone in that time. There's really 2 ways to do it. You can either draw the line so that it has a slope of 8.5, because remember, the slope of a position time graph is velocity. Or you can just kind of work through it, and you can figure out if I'm going 8.5 meters per second over 20 seconds, I just multiply the 2 together, and it tells me how far I've gone. All right, so if you're wondering where that 190 came from, I just multiplied the distance it traveled. All right. Now, velocity time graph, remember, is going to be a little bit simpler. Whenever it's constant velocity, the velocity time graph is just a horizontal line, because that horizontal means it is not changing. All right. And because it has some speed, we put it above the velocity of 0 axis. So right there, velocity time graph looks great. Now, I did draw a little doodle. I'd love for you to hopefully have drawn a motion map, and I'm going to cheat right away because I am not going to draw a straight line when I do this, which you should be staring at this and looking at horror. If you hopefully have kind of that feeling already, then my work is already paying off. So if I have this motion map, we know it's a constant velocity. So what you could do is basically you could draw, if you want, you could draw 20 dots. You could just draw a couple dots and have the distance between the dots be 8.5 meters. It's really up to you, but basically we know it's a constant velocity, so it would have to look something like this. All right. And remember, once again, a motion map is just basically the equivalent of what would have been if something is leaking oil, and every second it drops in oil that lands where it was. But what we're just seeing, ladies and gentlemen, is once again the idea that these three things all represent the same motion of an object. All right? And we just want to get comfortable with the idea that we can draw it multiple ways. Now, for the last piece, part C, it says, using the constant velocity particle model, solve for any unknown quantities. Show your work and use units. Now, what we're going to find out is that this type of question is actually one of the most important questions you will ever run into in your scientific career. All right? And it's because it's so vague. All right? In the public school system, not to get on my soapbox, but we're kind of trained to answer a very specific question that gets asked to us. You know, questions that involve maybe heaps of watermelons that are in a cart, or talking about, you know, someone's aunt is walking at a certain speed and they're trying to go to the crochet store. Very strange situations where it's very clear what you're looking for, and it's very clear when you've gotten to the end of the question. But in reality, there is no way for us to know what exactly is the end goal for a lot of questions. All right? So we want to get comfortable in this class with looking at a question or looking at a scenario and basically using every tool that we have available to calculate something. All right? Because we might find out the more stuff we calculate, the more that we start to know, the more we can kind of model how that object is going to move. All right? And as we start to do more labs, more projects, it's going to be very useful for us to figure out how we can calculate new quantities, new things about physics that tell us more things about how something will move. All right? Now, in this one, we're going to find out it's pretty simple, because the only really things that we can know, if we write down some stuff, we look at the right here, some of the things that we know. We know that the dune buggy travels for 20 seconds, so we know time. We also know that it's going at a speed of 8.5 meters per second, so we know its speed. All right? Which means we're just trying to figure out maybe what things could we kind of determine from those two things. And what we're going to find out is that if we look at the definitions that we talked about from the very beginning of this packet, we're going to find out that the only really thing we can calculate from those two things is the distance the car travels. All right? So, we know from the beginning when we define distance, the distance an object travels is really just equal to how fast it's going at speed times how long it's going at that speed. So, speed times time. All right? Well, we know the speed is 8.5 meters per second. We know the time, it's 20 seconds. So if we kind of use our little formula here, do a little bit of math, you'll get, and take like 30 seconds to kind of run through that. All right, but you should get that basically the distance this car travels is 190 meters. All right, and I kind of spoiled it earlier because when I did this graph, and if you do your graph correctly, you'll already have answered part C when you drew the graph, which is an important thing because sometimes when you see a question like this, you might also need to look back at what you've already done, because without knowing it, you might have revealed more information about this object than was given originally. All right, so with that being said, all right, this is our first kind of real practice of putting everything together that we've discussed, putting together our graphs and our calculation knowledge together to try and determine some more stuff about the motion of an object. We are going to keep practicing this as we finish up this unit and we go into our next unit. All right, our next unit is going to start discussing what happens when things aren't just going to constant velocity anymore, because when things are speeding up or slowing down, it acts a little bit differently. All right, but with that being said, ladies and gentlemen, that's where we're going to stop for this particular worksheet. If you have questions, shoot me an email, talk to me during office hours, or talk to me in class. All right, otherwise, I will talk to you later.